We've been learning about radiation and many of the properties of radiation. In our last video, we talked about what a black body is. Essentially, all objects in the universe, from a star to a molecule to a comet to an asteroid to people, you and me, everything emits radiation. And we talked about the theoretical concept of a black body, which is an object that emits radiation perfectly, meaning whatever energy it absorbs, it will also emit. And there's a perfect balance there. And that's what we call a perfect absorber and a perfect emitter. We saw that two of the main equations for this black body theory are Wien's law and the Stefan-Boltzmann law. Wien's law says that we can find the peak wavelength of radiation given off by any object based only on its temperature. And so we take the peak wavelength of radiation emitted is going to be 3,000 divided by T, where T is the temperature in Kelvin. Again, you must have the temperature in Kelvin. The Stefan-Boltzmann law looks at the quantity of energy that's emitted by that object. All right? The amount of energy given off in a certain amount of time is going to equal some constant times the temperature to the fourth. Remember, temperature still has to be in Kelvin, and this constant is 5.67 times 10 to the 8th watts per square meter per Kelvin to the fourth. Can be kind of confusing. Just remember this number, 567 million. That's what that number is, 567 million. Just indicates how much energy is given off in a certain amount of time. All right, let's do a couple of calculations. Let's start off by looking at our sun. The sun's average temperature is 10,340 degrees Fahrenheit. Now, what is that temperature? Well, we can do a conversion, and it comes out to be 5,727 degrees Celsius. We don't want this temperature in Fahrenheit or Celsius. We want it in Kelvin. So do one more conversion, and it comes out to 6,000 Kelvin. That is the temperature of the sun in Kelvin. And again, you've got those two numbers to be able to compare the 6,000 Kelvin to. So what is the peak wavelength of radiation given off by the sun? Well, here's our equation, 3,000 divided by the temperature. Just plug it in. What is 3,000 divided by our temperature of 6,000? Well, if we do that, then that gives us an answer of 1/2 or 0.5 micrometers. 0.5 micrometers, half a micrometer. Now remember that 1 micrometer is 1,000 nanometers, so half of that would be 500 nanometers. That is the peak wavelength of radiation given off by our sun. Well, what type of radiation is that? Where's 500 nanometers? Well, remember that 500 nanometers is the average wavelength of visible light. So where are we? 500 nanometers is actually here in the range of green light. The peak wavelength of radiation given off by the sun is green. Hold on, Dr. Olson, you say. The sun's not green, it's yellow. Well, it looks yellow to us because of our atmosphere. The atmosphere actually filters out a lot of the violets and the blues and even some of the greens. And so the next most intense wavelength after those three is actually yellow light. So that's why it looks yellow to us. But if we were to go out in space and have an instrument to measure it, we would find that the peak wavelength of light is indeed green. And you say, well, hold on, Dr. Olson. There are pictures of the sun from space. It doesn't look green. It looks white. That is because our eyes are seeing all the colors given off by the sun at once. And when we see all the colors mixed together, our brain interprets all those colors mixed together as white. That's why the sun looks white, even though from space it looks white, and from the surface it looks yellow, but the peak wavelength really is green. Now, the total side note here, but kind of fun to talk about all the same. This actually explains a lot of why plants on the surface of the earth are green. Why are plants green? Well, the peak wavelength is green. That's the most intense color of light. And so, actually, when you think about it, what we see is green. That means that the green light, that the light hits the leaf, reflects into our eyes. What we see is the green light being reflected off, but all the other colors are being absorbed. Plants have this chemical, chlorophyll, and it colors the leaves green so that it will reflect that green light away, keeping the plants from absorbing too much radiation. It's a safety valve. It keeps the plants from overheating and from burning. Then in the fall time, when the sunlight becomes a little less intense, the leaves change colors, and now that they're a different color, now they can absorb that most intense green light so that they can store up energy as they go into wintertime. Total side note, lots of fun to talk about, but no, you won't be tested on that particular point. What you would be tested on is this calculation. The peak wavelength is 3,000 divided by the temperature. All right, move on to the next one. How much energy is given off by the sun? Here's our equation. The rate at which energy is given off is going to be a constant times temperature to the fourth. So we just do that. 567 million, remember that's our number, times 6,000 to the power of 4. So in your calculator, just fine, 6,000 to the power of 4, whatever that is, multiply it by 567 million, and you get this huge number. Let me just interpret this for you. That's 735 septillion watts. That's an incredible number. That would be 735 billion quadrillions. It's a lot of energy that the sun gives off. Okay, let's do another example. Let's look at the Earth itself. The Earth's average temperature is 59 degrees Fahrenheit. That's if you average all latitudes, front and back of the Earth at any given time. The average temperature of the Earth is about 59 degrees Fahrenheit. That's 15 Celsius or 288 Kelvin. So what's the peak wavelength? 3,000 divided by 288 is our temperature. And we get 10.42 micrometers. All right, so remember that infrared, as we indicated here, is roughly 1 micrometer. Microwaves are 1 millimeter, a little bit bigger. So we are in the infrared range. The Earth gives off infrared radiation. Have you ever seen someone use an infrared gun? It's just a simple device where they point this device at an object and they can detect the temperature of an object. How do they detect the temperature? Well, they're picking up infrared waves, and based on the wavelength, they can determine the temperature of the object. But it's an infrared gun because it's only looking at infrared waves, because that's the type of radiation that all objects on the Earth emit. All right. Now let's talk about the rate at which the Earth emits radiation. Again, here's our equation, but this time we are putting in the temperature of the Earth, which is 288 Kelvin. And when we do that calculation, we get 3.9 times 10 to the 18th watts. That'd be 3.9 quintillion watts. Nowhere near as much as what the sun gives off, but it's still a fair amount. Far more than your 100-watt light bulb that you have in your homes. Now, take a look at this figure on the right, and you see, sorry, I turned off my laser pointer. Let's turn it back on. There we go. Here's the sun. Peak wavelength is in the green spectrum, and you can see how much radiation it gives off with this number of 10 times 10 to the 7th, about 10 to the 8th. And the number that's calculated here is a little different than what we calculated, but that's okay. It gives you a good idea. Then compare that to the Earth down here. Peak wavelength, a the amount of energy given off is down to 24. That's a far cry different from this, which is 100 million. That's what that number would be. 100 million would be the peak of sunlight. 24 would be the peak for the Earth. That's the amount of the rate at which energy is given off based on the way they calculated it for this figure. Huge difference. So the temperature matters not only in the type of wave radiation given off, but it also determines how much energy is radiated away. So here is a good summary of what we saw. The sun has a temperature of 6,000 Kelvin, gives off a peak wavelength of half a micrometer, which is 500 nanometers. The Earth's temperature is 288 Kelvin, giving off a peak wavelength of 10.4 micrometers. That would be infrared radiation. Now that we've learned a little bit more about radiation and black bodies, we are ready now to jump into the greenhouse effect and talking about how this radiation coming from the sun, how it affects the atmosphere and us here at the surface.